let's get some practice doing 3D sketches of organic molecules. I have shown here a number of condensed formulas, and so let's get some practice drawing Lewis structures, and then from there drawing 3D sketches. So the first thing we want to do is take this condensed formula and show its connectivity, show the skeleton of the molecule. So the CH3 we could draw as having 3 hydrogens attached to the carbon, and then a CH2. Remember, hydrogen only wants one bond, so as soon as we attach it to the molecule, it's done with its bonding. And there's a third carbon, it's another CH2, and a 4th carbon, and then finally there's a carbon, and then a nitrogen. Okay, so we show our basic connectivity, our skeleton, and now we want to try and fill all the octets that we can. And remember, carbon wants to have 4 bonds. If it's going to be neutral, stable, it wants to have 4 bonds. And nitrogen wants to have 3 bonds and a lone pair. And so if we arrange it to be a triple bond between the carbon and nitrogen and a lone pair on the nitrogen, then that would satisfy everybody's octet, and it would make every atom neutral. We could count for carbon 1, 2, 3, 4. Carbon has 4 and wants 4. Nitrogen 1, 2, 3, 4, 5. Nitrogen has 5 and it wants 5. So both of those would be neutral. So we have our complete Lewis structure. Now, in order to do the 3D sketch, we need to consider the hybridization for each atom. So for every single atom, hydrogen, of course, doesn't undergo hybridization because all it has is an s orbital. There's no orbitals, atomic orbitals to mix, so it always just brings in its s orbital. So let's think about the hybridization. This carbon has 1, 2, 3, 4 regions around it, and any carbon that has 4 regions to accommodate undergoes sp3 hybridization. And so that's going to be true for every one of these carbons that has 4 single bonds. It's going to be sp3 hybridized. Okay, now we get to this next carbon. It still has 4 bonds, but the 4 bonds are arranged differently. They're grouped differently. And now we have 2 regions of electron density. We have the single bond and we have the triple bond. So when you have 2 regions of electron density, we need sp hybridization. And the same with the nitrogen. We have the triple bond and the lone pair, so it's sp hybridized. And now the hybridization is going to dictate the geometry, so now we can start to build our molecule. We know that sp3 means tetrahedral. In order to draw a tetrahedral atom, we draw 2 of the bonds in the plane, like so. We can draw the hydrogen and the carbon in the plane. Remember, this bond angle is about 109.5. So the way we draw that is, we know what 90 looks like. We draw it a little wider than 90. And the other 2 bonds are going to be down in this area. One's going to be a wedge coming out towards you. One's going to be a dash pointing away from you. So it doesn't matter which is which, but we draw 1 wedge, we draw 1 dash, and those are going to be the other 2 hydrogens. So there's our first carbon, and it's tetrahedral. So now we come to the next carbon, and the next carbon, we've drawn 1 bond in the plane already. Now there's going to be a second bond in the plane, and where's it going to go? Now we want to resist the temptation of drawing it out like we did in our skeleton here, because straight out here it would be 180 degrees, and we don't have 180 degrees. It has to be bent 109.5. So that means we can either draw it in this area, or we could draw it on this area, your choice. Let's go down here. Okay, and if these are my 2 bonds that are in the plane, that means my wedge and my dash are up in this area. Again, doesn't matter which one is the wedge and which one is the dash. There are my 2 hydrogens. Okay, now we come to our third carbon. This bond is in the plane, so the second bond is either up this way or down this way. And we're going to kind of end up having a bit of a zigzag shape to our molecule. So I did this one up, so I'll go to this one down and this one back up. My dash and wedge are down here. One, two, three, 1, 2, 3. This is my last CH2. So here's my first bond. Here's where I can draw my second bond in the plane. So my wedge and dash are up in this direction again. So notice when I have a zigzag up, my dash and wedge and up. When I have a zigzag down, my dash and wedge are down. Okay, 1, 2, 3, 4. 1, 2, 3, 4. And now we're ready for our sp hybridized carbon. And what is the geometry for sp? When you have two groups, we put them linear, 180 degrees. So here's the first bond. So the second bond continues in that same direction. And the nitrogen is also sp hybridized. So what you could do is you can kind of draw a line continuing out and put the lone pair at the end of that line, or you can kind of draw the sp orbital in the plane in that direction and put the lone pair there. Either one of those would be good. But we also want to show these pi bonds. We have two pi bonds and we need to show that electron density here. So remember, the way we make a pi bond is we have two aligned p orbitals that are overlapping. So if this is my x-axis of the p orbital that was used to be hybridized, then the py is going to be perpendicular to that. So we could draw a py on the carbon, on the nitrogen, show them overlapping. Sometimes people like to put a lone pair here, kind of two electrons here rather, to represent the two electrons being shared as a pi bond. And then the second pi bond is going to be perpendicular. The p lobe is coming straight out and then straight back. So maybe we can show that with kind of a wedged lobe and a dashed lobe sticking back, and whatever we do on the carbon, we'll do the same thing on the nitrogen, and then show them overlapping to represent the second pi bond. So that's kind of what our triple bond looks like. And a way to confirm that you've drawn a proper 3D sketch is to build a model. So here's a model of this molecule, and now notice this has lots of different conformations. So there are actually a lot of different drawings that you may have for it. But if we line it up the way we did, we kind of did a zigzag. We started up here. I'm sorry, we were like this. Okay. So we started down here, we went up to the CH2, down to the CH2, up to a CH2, and then down, and then straight down in that direction. Looks very similar to what we drew. And again, we'll note that when we have an alkane chain like this, sp3 hybridized carbons, a lot of times we draw it in this zigzag. It's a little easier because if you don't keep going up and down, you can have the molecule kind of crash into itself. So this is really the most stable conformation, is the zigzag. And when we have a zigzag up, our dash and wedge are pointing up. And when we have a zigzag down, our dash and wedge are pointing down. Okay, so let's take a look at another molecule. Okay, we'll follow the same approach. The first thing we want to do is show the skeleton, the basic connectivity. So we have a CH3 here. And then we have a CH. Doesn't matter the angles that you show in this basic skeleton, because we're not trying to show geometry yet, so you could just do up, down, straight across, doesn't matter. Then we have another CH, and then another CH, and an oxygen. Okay, so definitely missing a lot of octets. We're going to have to add in some lone pairs, some pi bonds, to make every atom have its octet and have a stable configuration. And so, remember, carbon likes to have 4 bonds, so I think one thing I can do is both of these carbons are missing a bond, so if I put a pi bond between these two to make a double bond, then that would satisfy both of those carbons. So this has 4 bonds, this now has 4 bonds, this has 4 bonds, and then what we could do on this end carbon is the same thing with the oxygen. We can form a double bond between the carbon and oxygen, so that carbon has 4 bonds. And what's the oxygen missing? Oxygen likes to have 2 bonds and 2 lone pairs. So we'll add on those lone pairs, and now it's got an octet as well. Okay, and that would have the right formal charge, 1, 2, 3, 4, 5, 6. Oxygen has 6, and it wants 6, so that would be a neutral oxygen. Okay, so really the lowest structures we should attempt to do by inspection, rather than adding up all the valence electrons and putting them in and so on. With experience, we should be able to put these together fairly rapidly. Okay, how about the 3D sketch? Now again, atom by atom, we want to determine the hybridization, because that's going to give us our geometry. So our first carbon has 1, 2, 3, 4 regions of electron density, so that is sp3 hybridized. Here we have 1, 2, 3 regions of electron density. That gives us sp2 hybridization. And notice if I kind of add up the exponents here, if I have 1 s and 2 p's, that is what gave me my 3 hybrid orbitals to accommodate the 3 regions of electron density. So hopefully this is something that ends up being somewhat intuitive. This carbon has 3 regions, so it's sp2. This carbon, sp2. And the oxygen has 2 lone pairs and a double bond. We'll count all those as separate regions, so it's also sp2. We have a lot of sp2 atoms here. Okay, so we can start anywhere we want. Let's start with our, just go left to right again. So our tetrahedral carbon for sp3 is tetrahedral. So we draw 2 bonds in the plane, a little wider than 90. And 1 bond as a wedge, and 1 bond as a dash. That's what every tetrahedral atom is going to look like. Okay, so what we have to put here are 3 hydrogens and a carbon. Now, what you should do is you should put the carbon in one of these positions in the plane, because what we want to do is put as many atoms in the plane as possible. If I put my carbon out here, you know, out in front of the board, now the whole rest of the molecule is going to be floating out in front of the page, and that's going to be impossible to draw. So we want to locate as many atoms as possible in the plane, so let's keep the carbon chain in the plane. So then the other 3 positions are our hydrogens. Okay, now this carbon is sp2 hybridized. If you have 3 regions of electron density, you want to make it trigonal planar to get them as far apart from each other as possible. So we've already drawn 1 bond here, and now 120 degrees, we go down and up. It's about 120. Again, you know what 90 looks like, so we want a little wider than that. Really, 120 looks very much like 110. There's not going to be a big difference there. So we have a hydrogen and a carbon that we want to put in. We have a little more room to work down here. So let's put the hydrogen up here and the carbon down here. Okay. And this next carbon is also trigonal planar. So we'll draw a bond straight down and up that way. That's about 120 degrees, corners of a triangle. We'll put the hydrogen down here and the carbon up here. And then finally we have an oxygen and a hydrogen, another trigonal planar. Doesn't matter which way we put them, who's where, it's all good. Okay, now we want to show our pi bonds. We have a double bond between these 2 carbons and between the carbon and oxygen. And again, if we draw the trigonal planar in the plane like we've shown, then the p orbitals are orthogonal to that. They're perpendicular. They're going to be sticking straight out and straight back. So we could draw them as a wedge and dash on each carbon. There's 1 pi bond. And then on the carbon and oxygen, wedge and dash. So it's like we're tilting it just slightly so we can see both halves of the p orbital. And then how about these lone pairs? They're also trigonal planar, so they're in this region. We can kind of draw a line and show them. Last one example, we showed the orbital. Another option, sometimes you could just draw a line to show, not as a bond, but just showing the geometry that it's in the plane. Okay, and if we take a look at a model of this, okay, we have it flipped over here, trigonal planar, trigonal planar. This part of the molecule is flat, and you can see the zigzag shape there. And this last carbon is tetrahedral, and we could rotate it any way we want. We had it the one where the hydrogen is up here. Okay, you could have also chosen to put this CH3 group up here. That would actually be a different molecule, so it's kind of bent this way. This we call a cis conformation. This would be a trans conformation about that double bond. Those would both be okay, because this condensed formula doesn't tell us what shape the molecule is. We have a couple different options there. So those would both be acceptable. Okay, our next one's a little tricky because we have sodium in there. And something to remember about sodium, that's a group 1 element. When it wants to bond, when it bonds, it's going to form ionic bonds because it wants to form charged compounds. Charged species. So when you see an O and A, that means we have an O minus and an Na plus. It's actually a salt. So we'll have that as part of our sketch. So what else do we need to finish in our Lewis structure? We have lone pairs on that oxygen to make an O minus. We'll have 3 lone pairs to make our O-, and then these chlorines are going to have lone pairs as well. So let's try and jump right to our hybridization and to our sketch, because this is kind of similar to the ones we just did. This carbon has the 3 chlorines, and the carbon has 4 regions of electron density, so it's sp3. This carbon has 3 regions, so it's sp2. This carbon has 4 regions, the carbon, the oxygen, and the 2 hydrogens, so it's sp3. And this oxygen up here has 1, 2, 3 regions, so it's sp2. I'm not going to do the hybridization when all we have are lone pairs of electrons, because there's really no geometry to show there, because there's only one sigma bond. Okay, so our sp3 hybridized carbon, once again tetrahedral. So we draw 2 bonds in the plane. You can draw it pointing up or pointing down anywhere you want. And then 1 wedge, nice fat triangle there. And then our dash, make sure your dash is showing horizontal lines. Sometimes students draw dashes like this, but that would not be right. That kind of represents a partial bond, so make sure you're drawing horizontal lines there. Okay, so what do we have? We have 3 chlorines, chlorine, 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 and each of those chlorines has lone pairs, 3 lone pairs. The halogens need 3 lone pairs and 1 bond to be neutral and have a filled octet. Okay, and we don't need to show the geometry of those lone pairs, we could just put them on chlorine. Okay, the next carbon we have is trigonal planar, and so we want to do corners of a triangle, 120 degrees, oxygen, carbon, and then to show our pi bond, we show our perpendicular p orbitals, out and back. So there's our pi bond. Our 3D sketch should show our pi bonds in there. And then our lone pairs. Last time we did it as straight lines. Let's show you the other option of drawing the sp2 hybrid orbitals. They look like floppy ears there. That's another way to show the trigonal planar on that oxygen. Okay, now this carbon is tetrahedral. So 109.5 here, and our wedge and dash for our 2 hydrogens. And then this oxygen. Now we need an O-, so the way you make an O- is you have a filled octet and with 3 lone pairs, 1, 2, 3, 4, 5, 6, 7. This has 7 electrons, oxygen wants 6, so that extra electron gives it a negative charge. And then the counterion with this salt is a sodium plus. So when we have an ionic bond, we just draw the plus and the minus next to each other. What we want to resist is the urge to connect them, because that would represent a covalent bond. And this is, in fact, an ionic bond. So we want to make sure we draw that properly. Okay, again, this model, we have our planar sp2 hybridized carbon in the middle here, and then the tetrahedral with the oxygen, and the tetrahedral with the 3 chlorines represented there. Okay, now this next molecule is pretty interesting. It's really quite interesting. When we draw out the skeleton, we have a 3 carbon chain, 2 hydrogens on each end, and so right away we see none of the carbons have a filled octet. They all need 4 bonds. So the way we can achieve that is to make this a double bond and make this a double bond. Okay, so we have 2 double bonds on top of each other sharing the same carbon. This is called accumulated double bond. This molecule is actually called allene. So you can look that up and see some examples of that. The hybridization of these N carbons with 1, 2, 3 regions of electron density is sp2. These N carbons are sp2, and this middle carbon is sp hybridized. It has just 2 groups, so it's sp. So what's interesting about allene is most of the sp hybridized carbons we've seen have been triple bonds. This is an example where we have 2 double bonds, and we'll see what that does to the geometry. Okay, so let's start with our first carbon here. sp2 is trigonal planar, so we could draw that very nice in the plane, like so. Put our carbon here, and hydrogen, hydrogen. And where does our pi bond go? If we've drawn the trigonal planar in the page, then our p orbital is out here, perpendicular. And we can overlap them to form the pi bond. Okay, and then this carbon is sp hybridized. Sp means linear, so we can draw this straight out this way. But now, when we think about how to form this second pi bond, it's going to be another p orbital. Where is the second p orbital for sp hybridized? Sp hybridized atoms always have two unhybridized p orbitals. We've already shown the one that's in the x orbital, in the z orbital, straight out and back. So where's the second one? It's actually in the y orbital. It's in the y-axis, perpendicular in the plane. So if we draw that on each carbon, we see that's where this second pi bond is. So it turns out for alene, when you have accumulated diene like this, the two pi bonds are orthogonal to each other. They're perpendicular to each other. Which means now when we draw these hydrogens, if the p orbital is in the plane, what does that do to those hydrogens? They can no longer be in the plane. They have to be perpendicular to that. So it turns out that one is a wedge and the other is a dash. So alene has a twisted geometry. It is no longer planar. These two hydrogens are in the plane, and the other two hydrogens are perpendicular. And that's because here's the p orbital that connects to this carbon is in this direction, and the p orbital that does a double bond on this side is in this direction. So this is called alene, and it has this twisted geometry. Really interesting molecule when you consider the 3D sketch. Okay, and finally let's look at an example of a cyclic compound. This actually is benzene, six-membered ring with alternating pi bonds is known as benzene. And if we were to draw out our skeleton, we could show the carbons. This is a line drawing, so each of these junctions represents a carbon atom. It's a six-membered ring. So that means there's 6 carbons here with 3 double bonds. Okay, we have an OCH3 down here. And we have a carbon and a hydrogen. Okay, so that's our skeleton that we've drawn out, our basic connectivity. Now let's complete our Lewis structure. One thing that's missing here is with the line drawing. Remember, a line drawing, we're allowed to omit the hydrogens. We don't have to draw the hydrogens that are attached to carbon. So are there any hydrogens now we should fill in? Remember, every carbon wants 4 bonds. So it looks like these 4 carbons on the ends here have only 3 bonds shown. So they all need an extra hydrogen that was implied when we drew just the hexagon over here. So there's 4 hydrogens on the ring. And then how about this? These carbons don't have filled octets, so how can we take care of those and give them the 4 bonds that they need? How about adding a triple bond here? So we have that up here. And what's needed down here is just a 2 lone pairs on the oxygen to give it its filled octet. Okay, so hybridization. Before we do our 3D sketch, we need our hybridization. Our CH3 is sp3 hybridized because it has 4 regions. Our oxygen is sp3 hybridized. How about the 6 carbons on the ring? Every one of them has 1, 2, 3 regions, so they're all sp2 hybridized, trigonal planar. In fact, trigonal planar, the drawing we've already done is pretty much the 3D sketch. It, is pretty much the shape of benzene. It's planar, and we have all those 120-degree bond angles. Okay, how about this top carbon? has just 2 regions of electron density, so it's sp hybridized, and this other carbon is sp hybridized as well. Okay, so let's come down here and draw our sketch. So we can start with the ring, and as best we can, we'll just draw a nice hexagon. That would give us all 120-degree bond angles. There's a carbon and an oxygen on the top and bottom, and there's hydrogens in every other position. So as best we can, it really helps to do your 3D sketches in pencil so that if you realize you've drawn something that's not quite the right angle, you need to adjust it, you can erase it. It's tough doing it with a Sharpie marker, that's for sure. Okay, and what do our pi bonds look like? Our pi bonds are going to be p orbitals. So it turns out that with benzene, every single atom, every single carbon on benzene has a p orbital. So we could draw those in. They're all perpendicular to the plane. So just draw them all at the same angle because they're all parallel. And then here we're connecting these top 2 and these side 2 and these bottom 2. Something like that. Okay, how about our oxygen? Our oxygen is sp3, it's tetrahedral. So we draw it again with a little wider than 90 degrees. Now, because all we have are lone pairs here, we can draw those as a dash and wedge. But usually we don't refer to an oxygen as being tetrahedral, we describe it as being bent, because all you really describe for the geometry are the atoms, not the lone pairs. So comparing the carbon-oxygen-carbon, you describe it as being a bent shape. And then our carbon is also tetrahedral, so pointing up or pointing down doesn't matter which way we go. But one more bond is going to be in the plane, and then we have a wedge and a dash for our other 2 hydrogens. So there's our CH3, our oxygen, our ring, and our carbon. And how about this second carbon? Where are we going to draw that? What's our geometry for sp? Every single atom you draw, you have to think about where it goes before you draw it. So it's sp, so that means it's linear. So our first bond is here. Where's the second bond? Straight up. Straight up. So that's the shape of our molecule. And the hydrogen, straight up again. So sometimes you end up running off the page or hitting other molecules if you don't plan correctly, but that's okay. So how do we draw our triple bond? 2 pi bonds means we need 2 sets of p orbitals. So here's our first set perpendicular to the sp. And then the second set we can make it parallel to these other guys, wedge and dash, wedge and dash. And there's our triple bond. Okay, so here's our molecule. I think I lost a, I didn't have something attached down here. There we go. So here's our benzene ring. Notice benzene ring is totally flat because all the atoms are sp2 hybridized, and we have the triple bond extending from there, so that's going to go straight up. And then imagine this a different color being oxygen, these just lone pairs, and then we have our tetrahedral methyl group. Okay, so working with the models really helps confirm the fact that you've drawn a reasonable structure. If you have some strange bond angles or something that's not right, you're not going to be able to get your model to fit it. So that's a really great way of practicing it. So we'll make sure we have a complete Lewis structure, assign our hybridization, and do our geometry atom by atom as we build up a more complex molecule. Alright, good luck with your drawings.